In our final chapter of this course, we consider modern cosmology, the overall structure and development of the entire universe. We'll be concerned with the biggest structures, like galaxies and space and time itself. We'll investigate the history from the very moment of creation right up to the present time. Now, the ideas associated with the universe can be very strange, more strange than some of the things we've talked about already. So don't be surprised if you're a little bit confused about some of the ideas that we're grappling with and trying to understand our universe. And I'll be going a little bit back and forth between looking at the big picture and then looking at some of the micro details of the earliest moments. So we go from extreme compression of time at the early moments of the universe that are shorter in scale than anything you're used to time dilation, so to speak, and at the cosmological realm, which is where we are today in the development of the universe. So let's go along and enter into this exploration of our amazing universe. I like to start by considering a couple questions that you've probably all thought about at one time or another. And it just kind of reveals the difficulty of understanding the reality of the universe we live in. And it's the edge center problem. Does the universe have an edge, for instance? Well, here's a picture of a supercomputer simulation, a large-scale structure of the universe. If the universe has an edge, this is not it. It's not here or here. The edge, if it had one, would not be just slicing right across through a galaxy cluster. And then there's just true nothing demarking those two realms. So common experience, however, says yes, because it's kind of hard to conceive of anything not having an edge, right? But what would it be? The edge of matter? The edge of space? Those are two possible differences, right? Or are they? And then what would be beyond this edge? So if this is the edge here, you look to the right, there's the universe in all its magnificent glory. And to the other side, you look to the left, this way, well, what would you see? What would be there? Would it be a brick wall? That certainly isn't nothing, is it? Could you stick your hand into it? If you could, then there's at least space there, so it wouldn't be the edge of space. So it's really kind of confusing to contemplate what it might be. What is common sense and reality leading us to? Edge or no edge? I would suggest perhaps no edge, because then you'd have to have truly nothing and try to imagine what that is. Now, space may be infinite. No one on the planet knows whether space is infinite or not. The theories don't tell us one way or the other definitively. So you could speculate that it is. You could also speculate that it's not. My own philosophy is in line with there not being an edge, or not being infinite, I should say. Just because I don't think there's actual infinities in our observable universe, or the universe that's not observable as well. So, but that's something that I can't prove any more than someone can prove that it is infinite. And does the universe have a center? It's a related question. Well, is this the universe here? Is that it? Don't ask me why I put that graphic in there. It just looked kind of cool. So if that's the universe, common experience again says, yes, of course it has a center. I mean, I can see it right here, right about there, yes? Well, all objects with edges have centers, right? If an object has an edge, and you can see this edge here, if this is the universe, then the center is right about there, because you can see the edge. Problem is, this edge is not an edge like you're looking at there. Now, if it has a center, it needs an edge. So if this is the center, the only way you can define the center is in terms of the edge. If there is no edge, then how would you define the center? Take a look at your laptop. You see the edges? Point to the center, or can contemplate where the center is. You can do that real easily, but the only way you can do that is because you see the edges. Now, the universe having no edge, therefore also has no center. Those go hand in hand. Now this is also in line with what's called the cosmological principle that says that on large scales, as we observe the large-scale structure of the universe and consistent with general relativity, that the galaxy distribution is smooth, the matter is evenly distributed, and there is no center or edge. A little bit more on the cosmological principle, namely any observer in the universe, wherever you're observing from, will see and experience the same basic properties for the universe. A couple specific points about this is the concept of homogeneity. The universe is homogeneous on the largest scales. The universe has the same properties locally as anywhere else in the universe. So here you can see, if you're over here, the universe looks the same as it does over here. So no matter where you go, it in reality has the same characteristics. And then isotropy, that on the largest scales, the local universe looks the same in every other direction observed for any observer. So anywhere an observer is, you look this way, this way, this way, this way, this way, and it manifests the same characteristics. Even though, from our point of view, looking at the screen here, we can see that this universe is not homogeneous. This is homogeneous. Do you see the difference? Well, the universe manifests itself to be homogeneous and isotropic. Kind of looks like this partial region here. Again, not trying to infer that this is the edge of the universe, but we can't show an infinite expanse here on the screen, can we? Nor would we even know what to do about that. Now, the Earth is moving, the Sun is moving, the Milky Way is moving, the cluster is moving toward with respect to the Virgo supercluster. There's all these relative motions going on. As a result of this motion, there is blue shift and red shift. With respect to what we're going to investigate a little more, the background radiation of the universe, which is a black body spectrum. And if you remove the motions, the blue shift and red shift, from consideration of the black body spectrum that we see in the universe in every direction, we see a very isotropic universe. Namely that the black body spectrum has a temperature that's uniform within 1 part in 100,000, which is very close to being the same temperature in every direction. So that's a black body and galactic isotropy. This galactic isotropy and the temperature isotropy needs explanation. We can't just say, oh, it just is. So we would like to understand why that's the case. The Big Bang Theory must be consistent with that consideration, and we think it is. Something called universality is that the laws of physics are the same everywhere. No matter where you are in the universe, E is equal mc squared. The universal gravitation constant, Boltzmann's constant, Planck's constant, fine structure constant. The basic constants of physics are the same everywhere. The periodic table of elements is the same everywhere in the universe. We can measure that and determine that that's true. Corollary to all this is that the universe can have no center or edge. Has no edge, or these ideas would not be true. No edge, no center. More on that to come. So let's consider cosmic expansion and the universe that we find ourselves in, how we can visualize it a little bit. We'll use the analogy of an expanding balloon with dots on this balloon. See what those dots are doing. Well, the dots are going to be representing galaxies, and as the balloon is expanded, the distance between the dots expands as well. In fact, all the dots are moving away from each other. Another analogy would be raisin bread. Put raisin bread in an oven, every raisin moves away from every other raisin as the bread expands. So this is what's happening to the balloon. The dots that are further apart recede from each other faster than the ones that are closer together. So if we consider A and D versus A and B, here A and B, well, A and D moved apart further than A and B moved apart. So that's how that works. There is no preferred point of view from any dot. Any dot you're on, you're going to look at all the other dots and see all of them moving away from you. And this is, I'm going to call this the bubble law. It's very similar to the Hubble law. Little play on words there. So here you are at dot B. You're over here at dot B, and you're observing what's happening to the other dots. Well, after 3 seconds from here to here, A and C, these two dots, are 3 centimeters away from you. So you're on B, you look at C, and you look at A. Both of them have moved away 3 centimeters in 3 seconds. So they're moving away at 1 centimeter per second. Now B and D, they are separated by more space, balloon space, rubber material. They're moving away from each other at 2 centimeters per second. So by just kind of logical consideration, if these, say, dot C is moving away from you at 1 centimeter per second, it's done that for 3 seconds, it's 3 centimeters away. If you reverse time, you get back to the point of origination, back to the point where they were together, and you have the age of the bubble universe, which is 3 seconds. And the expansion of the universe and the considerations for its age go in like manner. Now the balloon represents the entire universe here. The entire universe on the balloon. One thing to note is that the individual galaxies, they are not expanding. As you can see in this analogy, the dots aren't getting bigger and bigger. If you actually put dots on a balloon, as you would blow the balloon up, the dots would expand as well. In our universe, the galaxies don't expand because they are bound gravitationally. And it's the space in between the galaxies that's actually expanding. Now, where this analogy partly breaks down is that in our universe, we can't look from outside and see the universe. The space outside has no meaning. There is no space outside our universe. And the space inside, you can visualize that inside this balloon, there's space. Because we are three-dimensional beings that can observe this two-dimensional representation, visualize it as being 3 dimensions, and recognize that there is an internal center to this. But this is the universe constrained to 2 dimensions. And if you think of the entire universe being on the surface of this balloon is representing all, the surface of the balloon represents all the matter in the universe. And there's something really interesting that comes out of this. In fact, I'll let you in on a little secret. I will tell you where the center of the universe is. I really will. I'll tell you exactly where it is. If you can tell me what is the center city on the surface of planet Earth. So consider Earth and all the cities distributed throughout the surface of the planet. Tell me what the center one is. If you do, I'll tell you where the center of the universe is. You see the problem? If you are constrained to 2 dimensions, which in a sense the cities of the planet are because they're distributed on the surface, then it doesn't make any sense to say where the center city is. There is no center city. One city is just as center, quote unquote, as any other. Moreover, there's no edge. If you consider the surface of the planet, you'll never come to an edge when you're investigating the material on that surface. Now, we don't live on a 2-dimensional surface. We, in our universe, exist on the 3-dimensional surface of a 4-dimensional space-time system. So what we have to recognize is that the galaxies, the planets, the stars, all the stuff that we consider the universe actually is existing on a 3-dimensional surface in a higher dimensional system. Now that's something that we just have to accept. But it starts to give us an ability to contemplate just how it could be possible for it not to make any sense to discuss where the center of the universe is. Namely, that there is no center, and yet at the same time that the universe is finite. Now we can't visualize that because we're not 4-dimensional beings. We can visualize the 2-dimensional surface being 3-dimensional beings. And we're visualizing the center region, and basically we have some dominance over these 3 dimensions. Nevertheless, this hopefully gives you an expanded concept of how it could be that we could be in a universe that doesn't have a center, doesn't have an edge, but yet is finite. And in fact, if you really press me on this, I would say that the center of the universe is everywhere, and it's nowhere. Because in the beginning, with the Big Bang, you have matter, energy, space, and time all compressed to a very small region, but that region was everywhere. You can't get outside of it like we're doing with this balloon and observing it. You can't be outside looking in because there is no outside. The universe at the Big Bang was all confined to that singularity. There was no outside. Outside had no meaning. So if you want to consider that the center, then you have to say everywhere is the center. And if you think about it, that's consistent with every city on the surface of the planet Earth is just as much the center as anywhere else. So hopefully that gives you some food for thought on the nature of the universe.